Building a machine learning model is only half the job. The real question is, how do you know whether your model is actually good? Hello everyone, welcome back to lecture 5. In the previous lectures, we learned how linear regression works and how we can train a model to make predictions. But after training our model, there is one important question. How good is our model? For example, suppose our model predicts the price of a house. The actual price is 50 lakhs, but our model predicts 45 lakhs. So, our prediction is not exactly correct. But how do we measure how wrong our model is? That's where evaluation metrics comes into picture. Today, we are going to learn 4 important evaluation metrics for linear regression. Mean absolute error, mean squared error, root mean squared error, and R2 score. And after understanding the theory, we will implement all the 4 of them practically using Python. But first, what is error? Before understanding the metrics, let's understand what we mean by error. Suppose the actual value is 100 and our model predicts 90. The error is actual minus predicted. So 100 minus 90 will be equal to 10. So our model is off by 10 units. Now imagine we have hundreds of predictions. We can't look at every single error individually. So we need a single number that summarizes how well our model is performing. That's what these evaluation metrics do. First, mean absolute error, MAE. Let's start with mean absolute error. The word absolute is important here. Why? Because errors can be positive or negative. Suppose we have 2 predictions. Actual is 100 while predicted is 90. So the error is positive 10. Another prediction might be actual equal to 100 and predicted equal to 110. Now the error equals to minus 10. If we simply average this error, plus minus get cancelled and we will get 0 as the output. It would look like our model has 0 error, but obviously that's wrong. So mean absolute error takes the absolute value of each error. That is, it removes the negative sign. So the formula is the average of absolute actual minus predicted. So example I have given here is, suppose we have error like 10, minus 5, 20, minus 15. Taking absolute values of it, we get 10, 5, 20, 15. Then we will do the average of it, getting value 12.5. which is our mean absolute error. That means, on average, our predictions are off by 12.5 units. Next is mean squared error. Now let's move on to mean squared error or MSE. Mean squared error works slightly different. Instead of taking absolute values of the error, we square the error. So the formula is the average of actual minus predicted square. So why do we square the error? So there can be 2 reasons. One being that squaring makes all the errors positive. But there is another important reason. Squaring penalizes large error more heavily. Example, imagine 2 error, 2 and 10. So if we use absolute error, it will just be 2 and 10. But if we square them, like mean square error do, it will be 4 and 100. So look at the difference. The error of 10 becomes 100. So mean squared error gives much more importance to large error. So this means that if our model makes very few large mistakes, mean squared error will increase significantly. So mean squared error is useful when large errors are particularly undesirable. Now let's compare them. Mean absolute error and mean squared error. error. Suppose our model makes these errors 2, 3, 20. MAE looks at it as 2, 3, 20 only. But mean square error looks at 4, 9 and 400. So it heavily penalizes that error of 20. That's the key difference. MAE treats error more linearly, while mean squared error gives more weight to the large error. I hope you understand. Let's move on to the third evaluation matrix, root mean squared error. Root mean squared error is simply the square root of mean squared error. So the process is, first we calculate the error, which is difference of actual minus predicted. We then square them, we take the average of it, and finally take the square root. So why do we need root mean squared error if we already have mean squared error? Because of the units. Suppose we are predicting salaries in rupees. The errors are measured in rupees, but when we square the errors for mean squared error, their unit becomes rupees squared. So that's not very intuitive. Taking the square root brings us back to the original unit. So root mean squared error is easier to interpret. The final one is R2 square. Now let's move on to the fourth matrix, which is also called as coefficient of determination. Unlike means absolute error, mean squared error and root mean squared error, R2 doesn't directly tell us the average size of the prediction errors. Instead, it tells us how much of the variation in the target variable is explained by our model. Simple explanation we will see. Let's say we are trying to predict a student's exam score based on number of hours they have studied. So if our R2 square is 0.80, we can say that approximately 80% of the variation in the target is explained by our model under the usual interpretation of R2. The remaining variation, which is 20%, is not being explained by the model. So it can be any factors, right? So the range is often between 0 and 1. An R2 of R square of 1 means a perfect fit, while an R square of 0 means the model is no better in terms of squared error comparison to the baseline that predicts the mean of the target. So simple way to remember all four. Mean absolute error. How much am I wrong on average? Mean squared error. How much am I wrong while heavily penalizing large errors? Root mean squared error. How much am I wrong with large penalty for large errors expressed in original units? And R2, how much variation in the target does my model explain compared with a mean prediction baseline? That's the easiest way to remember. I hope you understand this evaluation metrics for linear regression. In the next video, we will be practically implementing that code to make you understand it more efficiently.